Okay, thank you, Caroline. Hello, everybody. My name is Atticus. Let's go into the topic directly. But first, let's take a look into the content. Now, we have some introductions to serve as kind of a reminder to tell you why exactly we need cooling in the injection molding and what sort of a difficulty or problems, so to say, that is heavily related to the cooling stage. So after that, we're going to introduce you to the capabilities or the functions in Moldex3d to help you identify and re and to validate your new design of the cooling channels. And then we're going to do some special Moldex3d functions for the cooling stage. And then approaching the end, we have a case study, and right at the last step, we have the conclusion for today's webinar. Now, introduction. Now, why do we need cool? So, as you know, after the gate sealing in the injection molding stage, which means the part has undergone the filling and the packing stage, the part has to be cooled to suitable temperature for ejection. Okay, and the cooling occupies 70 to 80% of the entire molding cycle. So a well-designed cooling time will shorten the molding cycle time. Will shorten the molding time and enhance production. On the other hand, if you have a poorly designed cooling system, it will lead to multiple defects and also produce a very lengthened cooling time. Now, this is a graph showing you how much of the time that the cooling stage need, okay, in a visualized perspective. Okay, so after the mold close, you have the filling stage and then the packing. After the gate, then the boundary between the packing stage and the cooling stage is the gate sealing, hopefully, and we're going to take 70 to 80% of the cycle time to cool the whole part to the ejection temperature. Okay. Now, let's talk about the factors that would influence the cooling time and also the outcome of cooling. First, we have the product design. You have the thickness. Now, it goes without saying the thicker the thickness is, the larger the thickness is, the longer it requires to cool down the part. And then we're going to the material property here. So thermal properties of materials such as heat capacity, thermal conductivity of both the mold and par material can affect the cooling time. And then the mold design, how well you prepare a cooling channel, and the layout of runner system or the type in hot runner system. You also have another applications that would influence the temperature distribution inside the mold, as well as the choice of the cooler material for your cooling. And then the molding parameters, you have coolant temperature, mold temperature, and and as well as the time for mold opening and closing. The other there's one other point, one other factor in this topic, which is the spec. When we talk about to reduce the cooling time, we can also use other injection process like special injection process such as water injection, gas injections. Okay, Now, to because if there is a specific part that cannot be cooled down properly, okay, regardless regardless of the design or the design of the cooling channel or the molding parameters, that some product manufacturer would choose to use special injection molding to improve the situation with cooling. Okay. Now come to the let's come to the consequences of the poor cooling. Now I have divided the consequences into two parts, which is if you have poor heat dissipation, we might have a longer cycle time, or if you might have a high you might have a higher shrinkage rate, which means the part is very thick, and at that place, if the at that place it might create a seam mark because of the poor heat dissipation. On the other hand, we have the unbalanced cooling. I mean, between different mole halves, okay, which might leads to warpage. We'll take one closer look at each of them separately. Now, let's count. Let's go to warpage. Now, what you see now is that I have I, I set the mole temperature to be the same, the upper mole halves and the lower mole halves to have a 50 degree of temperature. Okay, to to ensure that you it doesn't to ensure the shrinkage, okay, between inside the part is uniform. Okay. On the other hand, if I set the temperature for the lower mole halves to be lower, now you now the up the upper part the upper part of the cavity, because they are experienced with they are experience a high the more heat there, so okay, so they can shrink more. On the other hand, the bottom half of the part, because they experience a low temperature, they shrink actually less, so you will create this kind of a smiley face distortion. Okay, so one thing to note is that during the temperature control system, we might want, in theory, we want to ensure that the temperature distribution in the mold is uniform. Okay. The other thing is cycle time. Okay. So you see two different layouts of cooling channels in in the category of numbers and the positions. Okay. So so in here in these regions we don't have any cooling channel, which means it will take very long path for the heat to transfer from the part to the cooling channels, which and you might also face the issue of heat accumulation. So it will, which means you will have, you will have high shrinkage rate and also longer cycle time. Okay. The other thing is the sink mark. Now, this is the plate that we have used in the experiment. On the backside of this four region that has been circled with red marks, there are ribs. Okay, so you can imagine in this junction with ribs, there are actually more volume or more mass of plastic metal in this region. Okay, so more mass accumulation, so to say. Now, if the cooling rate is not high enough, to bring the surface to a rigid state. Now, you would you the surf then the surface will have some sort of damp in it in the direction towards the rib, okay, towards the backside. So you have some sort of sink mark. Now, let's recapitulate it, the importance of cooling. Poor cooling process can lead to poor product quality, such as warpage, longer cooling time, and as well as sink mark. Now, what we can do is that you can use our functions to examine the factors of the cooling time and also to examine the potential defects so that you can redesign a new temperature systems and get rid of all those potential defects at the same time. Now, let's come to the cool capabilities. Now here I list 5, but there are, which I think is very important, but there are also some of them I didn't list it. So if you want me to talk about more, we can do it in Q&A sections about the cooling functions. Okay. So first of all is cooling time. Now, let's take a look at these two models. The only difference between these two is that there is a channel of cooling installed in the inside of this model. So stands to reason that the heat accumulation inside is heavily dissipated. Okay, so when you click on the cooling time result, you can see how you can see the time it requires for each area of the part to cool down to the injection temperature. Now, here 90% of the part it has for 90% of power to reach injection temperature, but on the other hand, in this new cooling design, only 2.4 seconds is needed. Okay, the other one is hotspot investigation. Now, what we call a hotspot is that it's the area that's about the ejection, that has a temperature distribution about the ejection temperature at a certain time step of cooling. Well, you can, whether it's the time step that you set or it's the end of cooling. Okay, let's take the end of cooling as example and click on the cooling time result. Okay, then you can use the psi function we call iso contour to examine which area has the so-called hotspot. Okay, so one of important, I would say, result that it can demonstrate is that to show you which area is still above injection temperature, and at the end of cooling, at the end of cooling time, you might want to avoid those regions. Okay, avoid to set a pin, ejector pin at those regions. Okay. Next one is the mode temperature distribution in 3 dimension. Now, again, this is the same model that we see in the first result, which is the cooling time. 2 models, one with the new cooling channel design. Now you can see it clearly the temperature in the mode distribution. Okay, to show exactly why the cooling time is heavily reduced, because now you have on the right side, now you have a new cooling channel. Most of the heat accumulation has been dissipated, has been gotten rid of. Okay, so you can easily find out the so-called heat accumulation area. and use this function to revise your design easily. Okay. The other one is mode temperature difference. Now, this is pretty much the same with the last one we talked about, but from a different perspective. Okay. So it gives us a direct value, okay, from the color bar. Okay. How, how large or how small the difference it is between the upper mode and the lower mode. Okay. So maybe you want to have a tolerance of plus minus 2.5 degree Celsius. Okay, you don't need to go to the last result item we talked about. You can just click on the mode temperature difference, and it will show you directly. Okay, and in this example, we have a K model of a syringe. Okay, and syringe with cooling channel, and the other one is without. Okay, so they have a clear temperature difference between the mode. The last one is the temperature at coolant inlet and outlet. Now, temperature difference at inlet outlet can be related to several parameters. Okay, for example, here we see the flow rate, and in this example, the difference between the flow rate is 100 times. On the right side, we have 1.2 cubic centimeters per second. On the left side, we have 120. Okay, and they produce a massive difference when it comes to the difference between coolant inlet and outlet. Okay, so now that this features this chapters it's dedicated for the features that we call it special core function in Moldex3ds. Okay, the first one is the transient cool approach. Now I'll explain to you what it is. Okay, it examine the temperature response time. So what I'm saying is that when I direct your attention to this chart, to this diagram here, now the initial condition of the mode temperature system is without a doubt the temperature you put in the process. It might be 20 degrees Celsius or 50 degrees Celsius. Okay, and once the injection cycle starts, okay, the temperature distribution will undoubtedly increase. Okay, and one thing to mention here, because you have the cooling channel installed in the system, so in the real time, it will create some kind of fluctuations throughout the whole site, throughout the production cycles, maybe 10, 15, 20 cycles. Okay, and once and you can see from the start of injection, you experience an unstable temperature rise, and then you can, and then you transition into the stable phase. Okay, yeah. So two approach we use here in the Moldex. Now the normal one is the average temperature. So it means during the injection, during the field pack cool, that the mole temperature distribution will be set to this average temperature. Okay, but when we use transient cool approach, that you can clearly see the progression of the temperature inside the mole. throughout the whole cycle, throughout the fill, throughout the pack and cool, such a such as this GIF file demonstrated. Okay. One thing that you can do is that you can set sensors, okay, on inside a mold or on the par to detect the temperature progression throughout different cycles, okay, to let you know if there is some kind of a huge fluctuations and that could affect the quality of the end product or the filling behavior throughout each cycle. The, the other one is mold preheat, okay? We consider actual mold preheat effects before actual injection process. Okay, so this one we know that in practice, molders will heat up, will do the mold preheat, okay? So the mold, this function shows you the temperature distribution inside the mold and also the progression of the temperature, okay, like such as this chart. So, and throughout this function that we can examine what kind of effect it will have on the temperature system and for the and what kind of effect it will have on the following injection. So it, because temperature system will have influence on the flowing behavior of the melt. Okay, and one thing just to mention here, when we use smoke preheat, we have we we have to take the transient cool approach, like the last slides. Okay. The third one is the cooling channel analysis for conformal cooling. Okay. We can predict pressure loss, velocity, temperature distribution inside the pipes of cooling channel. Okay. So what does it mean when it comes to conformal cooling? So the conventional cooling channel you see might be this kind of a design. Okay. And one the the advantages advantage of it is very easy to produce. Okay. On the other hand, you have different distance from the par to the cooling channel. So it might have in some extreme cases different cooling rate, so to say. Okay. The purpose of conformal cooling design is to get rid of this is to make sure that the different cooling rate due to this distance issue is completely re, re- completely gotten rid of, or at least reduced to a minimum. Okay. Let's take two examples here, which means this one and this one. So as you can see, most of the water in this cooling channel is flowing in this direction, and hence create this sort of we would so-called dead water zone. Okay, so the speed is horribly low, and there is no water, water coming in and out in this area. So creates poor heating effect. Now the other one is that you have a very complex cooling design. Cooling, yes, to cool down the par. Okay. So, and you can see here the blue, the color blue indicates the velocity of the coolant inside the channel. So in the last large chapter, we talk about the flow the flow rates. The flow rates, what is one of factors that influence the effect or the efficiency of cooling. Okay, so this so this function for cooling channel for conformal cooling channel is a very, I would say, a very good indicator for you to examine your conformal cooling design. Okay, that now we are coming to the very last part, which is the case study. Now we take the winner, which is the third prize of this year's last year, my bad, Global Innovation Talent Award. Okay, Minchi University did a study about the cooling functions. Now I'm going to explain you later about what they are actually doing, but a disclaimer here. So because this is a purely academic project, so some of the standards they use might be or it or use are different from what what is used in the com, commercial injection molding industry. So now they are trying to do a tooling. Okay, their purpose is to do to to do a tool to do three types of tooling. One with no cooling channel. The, the second one is with conventional cooling channel. Third one is with conformal cooling channel. Okay, so and to validate the results analyzed by by Moldex3d our software and practical experience in their lab. Okay, and also to have a better understanding of the conformal cooling systems to reduce warpage and cycle time. Let's introduce the part here. We have a thickness, overall thickness of 2 millimeter for the part. Okay, and they use a BLM mesh. Sorry, my total negligence. They use a design mesh of level 3. Okay, to do the solid mesh here. Now let's take a look at their layout of conformal cooling channel and also conventional cooling channels. Okay, for conventional it's very easy. One on the top, the other one below. For conformal cooling channel, you have one cooling layout on the inside of this cup model and one on the outside of the cup model. Okay. And they select the core side temperature and cavity side temperature to be 27 degree with a coolant choice of water. Now, let's take a look at their simulation result here. So with conventional cooling, you see the temperature difference, okay, between in the whole temperature distribution shows there is a range of 8.3 degrees Celsius difference. Okay, with the conformal cooling, we only have 0.173. Okay, and then when we take another closer look, we can see because in the conventional cooling, there is no layout inside the cup, so to say. So the temperature will start to rise, okay, from the bottom and to the very top, because in the very top, on the top, we have set a gate here, okay, to pour the melt inside the hollow space between upper mold and lower mold. The other one is mold temperature difference. Okay. Now you can see clearly with the conventional cooling, we have a 6.2 degrees Celsius of difference. With conformal cooling, because the channel covers the inside and outside of the part. So we only have less than 0.2 degree, okay, the temp. Then we can take another look in the chart, okay, to see how much time it actually needed in the simulation to, to cool down the to cool, to cool down the parts to the ejection temperature. Okay, so the first one is without any cooling channels. Second one is with conventional. The third one is with conformal cooling channels. Now, uh, they use because this is an academic research, so they selected the temperature at very low at a, at a very low value, which is 27 degrees. So the same with the mold temperature. Okay, but you can as you can see that it only took for the conformal cooling channel 92 seconds, but for the conventional cooling channels it took more than 300 seconds, and for the one without cooling channels, so a total of 950 seconds. Okay, and this is how much a difference you actually manifest if we have different cooling layouts. Okay, now here we have the conclusion. Now, Moldex3d Cool helps to validate and optimize cooling channel designs. Okay, so let's do a recapitulation. So we can talk about once you can use our software to run a basic diagnostic of the to run the simulations, which is a basic pre-diagnostic to examine whether or not there are some kind of a defects, okay, and to see if those defects are heavily related with cooling. Okay, so then you can you can do another cooling or temperature system to reduce or even completely eliminate the possible defects, okay, in on computer instead of cost wasting unnecessary huge amount of money to do on the mold trial. Okay. By using Moldex3d, you can have the distribution of the mold and part temperature and the possible defects. Okay, with this cross reference, you can see how the cooling system influenced the product quality.